Orpington. I was wrong. Marge the Americana. Americana. She's cute. She's cute. She has the prettiest feathers, I think. She's skittish. All right, now, let's create the distribution for Marge. Let's create the distribution for Marge now. I'm gonna mute the screen. Yeah, actually, I'll still. We'll leave it on behind us so we can refer to it if we need it. Okay, so plot number 3 is we're gonna buy 3 birds. And they're all called pullets. They're all called pullets. But that doesn't mean they're all girls. That doesn't mean they're all girls. That just means that they think they're 90% girls. So, my question for you guys is right now, what values of x do I now have for this distribution? 0, 1, 2, and 3, right? I picked up another possibility. I might not have any girls. I might only have 1 out of the 3. I might have 2 out of the 3, or I might have 3 out of the 3. Perfect. Perfect. Let's assign some likelihoods to these. Pick any one of those you want and give me what the decimal approximates. Richie!
For 0, it would be 0.1 times 0.1 times 0.1.
Wouldn't it now? Wouldn't it be 0.1 cubed?
Yeah.
1 in 1,000, babies. It's getting harder and harder to buy all roosters. Because in order to buy a rooster, you've got to get a rooster every single draw. That's not very likely. It's only 1 in 10 on every given draw. So drawing 3 of them is not going to happen but 1 in 1,000 times. So over the course of 1,000 years, if I send Max in every year to buy 3 birds, roughly once over that 1,000 years, if my son is Yoda, roughly once over that 1,000 years, he's going to pull three roosters on average. On average. Beautiful. Good. Pick another one. What's another one?
3 easy.
Yeah. 3 easy. Good. Now, are you realizing now on your last project why I focused on those 2? It was always alls or nones, or at least ones. But at least ones were also alls and nones. Yeah, that's why I stayed there on that project.
Yes.
So 3 is easy, Richie, because I'm assuming you did 0.9 cubed.
Yes.
I'm assuming, because you have to get a girl, and then a girl, and then a girl. So that means Marge is a girl, and Bertha's a girl, and Nancy's a girl. Or, in this case, Marge is a rooster, and Nancy's a rooster, and Bertha's a rooster. And what's that going to be? 73?
About 70.
Yeah, 72.9 if I do the math right in my head. So notice it's also getting harder to get all girls, as we said it would. Because every time Max goes back in the box to grab a bird, it's a roll of the die. Think about it this way. These chicks are 10-sided dice. Because that's what they are. They're 10-sided dice. 9 of the 10 sides have a G on them, and the remaining 1 has a B on it. So if you're buying 4 birds, it's like taking 4 dice and throwing them and seeing what you get. Or if you're buying 3, taking 3 dice and throwing them and seeing what you get. This tells us that roughly 73% of the time you're going to see 3 G's pointing up at you. This tells us that roughly 1 in 1,000 times you'll see 3 B's pointing up at you. How many times are you going to see 1 G and 2 B's pointing up at you? Or 2 G's and 1 B? Good! What do you say back? What do you say?
It will be 0.9 times 0.1 plus 0.1 times 0.9.
This is only 2 birds. It's only 2 birds.
Okay, so you'll do that square.
Oh, good! Everybody, time out. Perfect. Good so far? That's 1 girl and 2 boys. But now, Rebecca, what was this plus you were talking about? I heard you say plus? Nice and loud, sister. This is gorgeous. Nice and loud. Nice and loud. 0.1, 0.9, 0.1. And then wouldn't there also have to be a 0.1, 0.1, 0.9? Oh, yes. And Natasha has said, wait a minute, time out. I'm tired of this addition. Because it's going to get annoying. Imagine if your plot has 41 birds in it. There's too many additions. Think about it this way. This is the chance of getting a girl and 2 boys. The one thing it doesn't tell you is where the boys and girls are. But wouldn't it be the same? This right here, if I assign an order to my birds up here, this would mean that Bertha's the girl, and Marge is a boy, and Nancy's a boy. Well, wouldn't it be the same numerical answer if Marge was the girl, and Bertha and Nancy were boys? And wouldn't that be the same numerical answer as Bertha and Marge are both boys and Nancy is the girl? So Natasha's vote, and I like it very much, by the way, it wraps up Rebecca's vote beautifully by just simply placing a 3 out in front here. That was supposed to be blue. I want it to stand out. We'll make it red.
But it has to be 3. Sounds like the whole answer.
It's okay. It's all multiplication, so it's okay. Because if you're adding 3 numbers together, that's simply multiplying by 3. So what you're saying is correct. 0.9 times 0.1 times 0.1 plus 0.1 times 0.9 times 0.1 plus 0.1 times 0.1 times 0.1 is the same as 3 times 1 of those. And that's why you don't need extra parentheses or anything like that. There's no addition anymore. We took care of multiplication. I love what you're saying. It's correct. So in other words, this tells you the probability of getting that particular gender arrangement, and then this tells you how many different ways you can assign where the girl is. Is that fair? Could we have done that over there with our other distribution? I think somebody actually said we said to do that over here. You could just take this away and put a 2 in front. And that takes care of it, doesn't it? Mathematically, that takes care of it. I like the fact that we wrote it out, though, because it lets us see why the shortcut works. I always like to see why shortcuts work, as opposed to just going to the shortcuts. Fair enough? What's that end up being? 0.01, 0.009, 0.0027. Check my math on that one.
Can you take away the square, right?
I'm squaring it.
You're squaring it.
Well, because there's 2 roosters. If there's 1 girl, there has to be 2 roosters, yeah?
Right.
So that 1 in 100 chance has to happen. But then it's weighted by the 90% chance additionally that we get a girl.
Right.
Fair?
Yes.
Did I do this right? 2.7%?
Yeah.
0.0243.
Oh, 243. Well, thank you. Wait, you sure?
No,
That's 27. 3 times 9 is 27, yeah.
Sorry.
That's okay, don't be sorry. It's good. Statistically, it's equal. Statistically, it's equal. 2.4% versus 2.7% is let it go. But I do want it to add to 100% so you guys actually believe me that this is working. Many students kind of like, they're like, yeah, okay, it seems like a bunch of hand waving, but it's not hand waving, it's actually really good mathematics. If it doesn't add to 100%, you'll get pissed at me though. Fair? So this is pretty rare, yeah? 2.7%? I wouldn't expect that. If I went into the store with Max and he picked up 3 birds, I would be kind of surprised if I had 2 boys and a girl by the time they matured. I'd be like, what the hell? This is not rare at all. 73% of the time is actually very common, yes? But these are pretty rare. So now we know what the answer for 2 is. It's whatever's left, correct? To get to 100%. But let's do it computationally. This is kind of fun. Computationally, how would we do it? 2 girls and a boy. Austin, help me out.
Would it be 3 times 0.9 squared?
Okay, if you don't mind, let me build it piecemeal if it's okay. So Austin says 0.9 squared times 0.1. Is that legit, first off? That's 2 girls and the 1 boy left over. We have to have the 1 boy in there because he has to be a boy. But then Austin says 3. Are we buying the 3? It has to be a 3, doesn't it? It has to be. Because to assign, think about it 2 different ways. Let's pick where the girls are. Here's the 2 girls. Who can they be? Bertha and Marge? Who else? Marge and Nancy? Who else? Nancy and Bertha. That's it, 3 ways, right? How else could you view it even simpler than that?
There are 13.
Pick the boy. Pick the boy. Either Bertha's the boy, or Marge is the boy, or Nancy's the boy. Either you pick the chickens or pick the rooster, it doesn't matter, because there's only 2 outcomes. Either it's a girl or it's a boy. If you've assigned the girls, you've by default assigned the boys. Does that make sense? If I had to pick 27 people in this room, wouldn't it be easier just to pick the 3 I don't want, and whatever's left over are the ones I need? That's kind of the mathematical skill we're using right now. Not that I don't want any of you. You're all beautiful. I love you all. But it becomes mathematically easy to do it that way. So yeah, Austin, I'm with you, brother. 3 out the front there. Yes? Make sense? So that's what? 0.81, 0.081. Hey! 0.243? Rebecca, is this one you had?
Yeah.
Is that your... Yeah! I get this one now. Because that's 0.81, 0.081 times 3 is 0.243. Boom! Would I be allowed mathematically to act surprised if we bought 3 birds, got them home, fed them, took care of them for 6 months, and then I got a rooster and 2 hens? Can I go back to the store complaining and bitching and moaning about my rooster? What would the store owner be able to tell me if he understood mathematics? Which he now does. The guy who does arrangement now understands it. What's that guy's name? He's so cute. You know what I'm talking about? I want to say Elliot, but it's not Elliot.
Is it the guy that owns it?
The glasses? He's so cute. Oh. What's your name? You're awesome. Ah! But whatever his name is, would I have a case that I could be pissed about having a rooster and 2 chickens? No. This tells me that should happen about 25% of the time. That's hardly unusual. If you flipped 2 coins, and they both came up heads, would you think something was wrong with your coins?
No.
No, because that happens 25% of the time, yes? So does this. Essentially 25% of the time. In other words, the store will be like, that's fine, just go home. Go home. Yes, I know it's more likely to get all 3 girls, but that doesn't mean it's unlikely to get 1 boy. If you had 2 boys and a girl, I'd hear your case. If you had 3 boys, I'd really hear your case. But this is hardly beyond a reasonable doubt. This is court, right? This is beyond a reasonable doubt. Not beyond a reasonable doubt. Yes, beyonder a reasonable doubt. Totally within the realm of possibility. Totally within the realm of possibility. These are the outliers. That is not an outlier. So you can't complain with a flock of 3 and a rooster. Sure, it's unlikely. It's just not horribly unlikely. It's not horribly unlikely. How many of you guys are one of 2 kids? How many of you guys are one of 2 kids? Valerie, brother or sister?
Brother.
Brother? Okay, so there's a mismatch. Brother, sister?
Sister.
Sister. Is that weird? Do we riot because Natasha has a sister? No, because it's going to happen 25% of the time. Who else? Danielle, it's you. You and?
Brother.
You and a brother, there's a mismatch. Who else? Sister! I'm pissed again because it's row 1. These guys are weird because they have 2 sisters. No, it happens 25% of the time. Who else? Brother, mismatch? Sister? I'm pissed again. You see what's happening, friends? It's just as likely to have a mismatch as it is to have a match. And we are seeing, kind of disturbingly, alternating. Sister, same gender, different gender. Same gender, different gender. That's probability, yes? And I think everybody's okay with that? It's the same argument as why this isn't unusual. This is about 25% of the time. It's going to happen. If I send Max into the store 4 times and he buys 3 birds each time, expect in one of those 4 trips to come out with a boy. Now that should hopefully make sense. If he goes in the store 4 times and buys 3 birds each time, how many birds has he had altogether? 12 birds altogether, right? What's the chance of a girl again? Probability-wise of 1 girl? 90%, which means 9 girls out of every 10 birds. If I buy 12, I'm essentially due for a rooster, aren't I? That's why I was not surprised at all with your 3 roosters out of 18. It's 1 in 6. It should be 1 in 10, but 1 in 6 isn't that far away from it. Eventually, your luck runs out, and you have to have some boys. Nobody knows when it's going to happen. I mean, we could easily go into that store for decades, buying 4 birds at a time and never getting boys. But on average, over time, if you look at all the birds purchased from that store, you'd be amazed. Look at Craigslist. Please take my roosters before my neighbors kill me. Somebody got roosters at High Desert Ranch at home, and they're trying to get them for free on Craigslist. Because probability wins over time. Yes. You guys ready for one more flock?
Yes.
Let's do my flock now. Flock number 4, my flock. My flock. Here we go. Let's add Mary, the one who pecks my butt. Cooking or tilapia, for God's sake. Pissed. All right. Flock number 4.
Maybe she didn't want hers cooked.
They don't like it raw. Thank you for that. They don't like it raw. So we've got a pond, too, in our backyard. It's a 3,000-gallon pond. We've got a bunch of big goldfish in there. And koi. I put a bunch of feeders in 10 years ago, and now they're like, a foot long. We got crappie in there. Got some rainbow trout in there. They're all doing great. Every once in a while, one of them dies. And I assume that they would just peck through the remains. I mean, chickens are scavengers. They'll scavenge as much as they'll hunt. I've watched them eat lizards and frogs, too. It's disturbing. I mean, seriously, the whole dinosaur thing, like watching them chase a lizard down in their pen and rip its head off.
You can see how they claim that chickens are
Yeah, I believe it.
dinosaurs.
I believe it, little freaking velociraptors. So the raw fish in the pond flows to the surface, been there for maybe a day or 2. So the rigor mortis is set in, but I mean, they're scavengers, for God's sake. I watch them eat rotten fruit. Then I take it out and I throw it in their pen with them. It sits there for like 3 days. And then Max is like, can we cook that? I'm like, yeah, why not? Because I put the clothes on the nose and I get the fire going. We cook the goldfish on the fire. Because Max likes cooking stuff on the fire, whatever. Throw in the pen, they almost kill each other to get to that cooked goldfish. They won't eat raw food, raw dead fish. They'll eat cooked dead fish. And my butt.
Which is weird because they would eat each other.
I know! It's almost like fish are a different animal, so to speak. Yes. I'm not saying I understand it. I'm just saying it pisses me off. She bites my butt.
Either that or your chickens are spoiled.
Well, they are definitely spoiled. Yeah, they're definitely spoiled. Most of our animals are. But I'm a recovering vegetarian, former and current hippie, so all our animals get spoiled. So, although these making me rethink chicken soup. Not gonna lie to you. Okay, I never asked you guys a question. On average, how many girls should we have if we buy 3? Is it going to be 2.7? Remember, you add a girl, you add 0.9. Excuse me, you add a bird, you add 0.9 of a girl. So now we're up to 2.7 girls per 3 birds. Which means, if you buy 4 birds,
3.6.
your average is, thank you, Susan! Your average is going to be 3.6 girls per 4 birds. Now, this is the first time this has ever happened, where you could simply take the number of items in your sample and multiply it by a probability to get an average. And it's the only distribution this works for. This is a very special distribution called the binomial. I want to spend a lot more time on this on Thursday. Binomial, can you see why it's called binomial? 2 outcomes for every bird you buy. You buy a bird, it's either a boy or it's a girl. Now, I mentioned before that somebody correctly, I think, told me that 1 in 10,000 chicks have both male and female parts. And they do. And at the end of the day on Thursday, I'll show you that I actually made a distribution up for that. A trinomial distribution. Boy, girl, and other. And it's interesting. It's a really, really cool distribution. But it doesn't change. It doesn't change the distribution hardly at all because it only happens 1 in 10,000 times. It hardly happens at all. And I'll show it to you later. I'll prove it to you. It's less than 1% occurrence of what actually goes on. Let's go back to this now. You buy 4 birds. How many girls are you going to get? Good. I like where Bailey's going. She goes right back to this one, and she's like, okay, I can follow the pattern. Perfect. Good sister. 0, 1, 2, 3, or 4. Those are your outcomes. We happened to get this outcome. This last time around 3 years ago. Lord knows what's going to happen tomorrow night when he goes back and buys 4 more. We'll see. Let you guys know in 6 months. We'll trade stories at 244, Daniel. All right?
Yeah.
So, and we actually already calculated this one, didn't we? Beginning of class, we calculated this. This was the 0.9 to the 4th power that we did earlier, which was 65.61%. Are you noticing how that number is getting smaller with every additional bird we're adding in? Yeah, because every time you roll the die, there's a chance of that bee coming up. The only way that could stay the same or get larger is if there's a 100% chance of a chick being a female. That's not what I hear. What's the other one that's very easy to calculate?
0.
Are you guys concerned? This is almost never going to happen. 1 in 10,000 trials. Wow. That shouldn't happen. If you buy 4 birds and they're all boys, then you go back to the shop owner and be like, dude, what? Seriously, I think you're 90% off at this point. I think it's way lower than 90%. And you have a mathematical argument, don't you? This is what Math 244 is all about. Developing a mathematical argument to prove or disprove some theory that's being held. It's the whole point of hypothesis testing. Now, if that happens, you question the 0.9%. This doesn't mean it can't happen. It means for every time 10,000 families buy 4 chicks from the store over time, somebody, somewhere, has to get 4 boys. And when that person gets 4 boys, they get pissed. Now, the shop owner can come back with, well, you're just that lucky one. Out of 10,000, there's 9,999 other families that thank you for your purchase, because they don't have to get it. That's a perfectly mathematical comeback. I mean, what's his name? Elliot? Ian? He's adorable, the guy who looks at that, isn't he? Let's keep going. What's the chance of exactly 1 girl out of all 4 of them?
4 times 0.9 times 0.1.
0.1 cubed. So I'm going to start with that if it's okay. So I heard a 0.9, that's the girl. And then I heard a 0.1 cubed, that's the 3 boys. And then I heard a 4. Why 4?
It's because there's 4 different.
There's 4 places for the girl to be. Either that's Nancy. Nancy is the girl, or Mary, or Bertha, or Marge. There's 4 ways to have that girl assigned. Each one of the probabilities is this. So it's 4 out front of there. blues right here. 4. And half dead. So what's that end up being? 0.0009. Is that 0.0036? That shouldn't happen either. That's 36 times out of 10,000. So that shouldn't happen either. That's very, very rare. That you're going to buy 4 birds, 3 of which are going to be boys, 1 of which is going to be a girl. Should not happen very often. 36 times out of 10,000. Pretty rare. Pretty rare. So if it happens, you have a right to go bitch to your store. And again, Danielle, this is the number of roosters you got out of 18. It shouldn't happen out of 4. Out of 18 is perfectly logical. Fair enough? Okay, good. Let's jump over to 3, because I think 3 is parallel with that, isn't it? 3 is parallel? Go ahead, be brave.
Come on.
Flip the exponents, yeah? Thank you, Natasha. Flip the exponents. Now you've got 3 girls, so you got 0.9 cubed, which is at 72.9% from the previous, but you also have to have a boy, which knocks it down to 7.29. Multiply by what number to account for all the... Bailey's saying 4. Same logic, right? At this time, instead of picking where the 1 girl is, pick where the 1 boy is. Pick where the 1 boy is. The boy is either Mary or Nancy or Marge or Bertha. So you've got 4 here as well. What's that end up being? 28%?
29.16.
29, sorry? 1.6, thank you, friends. That was too many decimals to keep track of in my head. 28-ish. Do you have a right to complain if you got a boy and 3 girls? I don't think so. 29% is pretty high. That's 3 in 10 trials, roughly. So really, if that happens, that's like, well, it happens. I mean, yeah, it's more likely that you get all girls. But it's not so rare that you get 1 boy mixed in with 3 girls. Fair enough? Now, we know what this one has to be in the middle, because we can add up what we've got and subtract it from 100%. But let's figure it out, because it's more fun that way. Okay? And soon, you don't have to worry about any of it, because I'm going to give you software that does it for you. So, say that again.
0.09 cubed and 0.01 cubed.
Oh, that's 6 birds. How about both of them squares? Is that okay?
That's what I meant.
That's what you meant.
Not
Well, that's perfect then. Thank you, Serenity.
The 2, not a 3.
No, it's okay. Squared and squared. It's beautiful.
Times 4.
Times 4.
Times 6.
Times 6. Times 5. Those are numbers out too. What is it? I heard 4 and I heard 6.
4.
It's 4. Let's time out now. Friends, we got the bird pictures right here, yeah? All we've got to do is figure out where the girls are. Let's figure it out, right? Amaya saying it's 6. I'm hearing 4s and 6s. I love this. We should put 5 and call it an average. Let's figure it out. Let's assign the girls. You guys tell me. Who's the girls? Top 2. Who else could be girls? Who else could be girls? Left side 2. Who else could be girls? Who else could be girls? Who else could be girls? Hot damn! Are there any more than that? That's it. That's it. There's only 6 ways to grab 2 of them at a time. There's only 6 ways to grab 2 of them at a time. The mathematics, that is 6 there in the middle there. That's 6. The mathematics behind why that is 6 is covered in more detail in your project that's due on Thursday, should you want more mathematics. It's my opinion you don't need more mathematics if you can do what we just did. Please, Natasha.
With a bigger set, how would you figure that out?
That is the most awesome question so far. What if we have 18? What if there are 18 birds and you have to have 9 of them be girls and 9 of them be boys? Hold that, give me 2 minutes on that question if it's okay with you. That's a fantastic, best question. Over to here, what does that work out to be, friends? Do you have a right to complain? Let's see. About 5%? 0.4816? If I did that right? Do you have a right to complain? There's a screen there.
Yep.
Do you have a right to complain?
Yeah.
That's pretty unusual, isn't it? Just so you know, FYI, and we talk about this at length in 244 and why sometimes it's not always the best case. Anything under 5% in a distribution is called unusual. That's fairly industry standard. It corresponds to what's called 95% confidence or a 5% significance level. So pretty much all of these events would be considered unusual by the 5% rule. Although this one's getting close to 5%. In other words, I wouldn't complain as vehemently for that one, obviously. I would bitch if I had 4 roosters. Like, what the hell, dude? But the 2 and 2, it's tricky. It's tricky. The 3 and 4, you got no complaints. Probabilities are too high. The 2, we're starting to toe the line a little bit there. Now, Tashi asked me a very good question. Okay, so the only way to be able to calculate these numbers, these 4 6s and 4s, is to actually have pictures of the chickens in front of you, yeah, and then work through them. Now next week, I'm going to have a quiz posted for you guys that gives you a little bit of math history that explains where those numbers came from. This is my first part of my answer to your question, which is a very good question, by the way.